In this example, we are going to analyze the function g of s. G of s has two poles at 1 and one pole at 10 radians per second. We're going to come up with the Bode plot for this first, and then see if the system is closed loop stable, and back that analysis up with either Nyquist or Routh locus. If you want to use this function to plot the Bode plot, we have to rewrite this in the standard form, and the standard form will be 2 over s plus 1 squared s over 10 plus 1. I factor out 10 here, we get s plus 10 divided by 10 plus 1, 20 divided by 10 is 2. Now we can start the Bode plot. We have two cutoff frequencies, 1 and 10 radians per second. We have no poles at the origin, no zeros at the origin, so we can start at very low frequencies, to the left of all cutoff frequencies. The lowest frequency here is 10 to the power of negative 1 radians per second, to the left of all cutoff frequencies. At that part of the Bode plot, the only thing acting on the Bode plot is the gain of 2. So the only thing acting on the Bode plot will be 20 log of 2, which is approximately 6 dB. So the Bode plot will start at 6 dB, and we will stay at 6 up to the first cutoff frequency, which is located at 1 radians per second. This is 6 decibels. What happens at 1 radians per second? Well, there we have two poles, two real poles at the same cutoff frequency. Each pole adds negative 20 decibels per decay to the slope, so the slope that is 0 becomes negative 40 dB. Which means that when we are 1 decade from now, so we are at 1, 6 dB, when you are at 10, we are at 6 minus 40, because you are moving on by a factor of 10 in the frequency. We go down by a factor of 40 decibels per decade. Why 40? Because you have two poles at 1, each pole contributes with negative 20 dB per decade. So what is the magnitude at 10? Well, if here we are at 6, at 10, we should be at 6 minus 40, because this is negative 40 dB per decade, this is 1 decade, this is 40. So here we should be at roughly 34, negative 34 dB. Alright, so this is a decay of 40 for a jump in frequency of 10, 1 decade. When we are now at 10, here is another cutoff frequency. And this cutoff frequency comes from another pole. What happens? The pole adds negative 20 decibels per decade to the current slope, which is negative 40. So that becomes negative 60 dB per decade. Moving on by a factor of 10 in the frequency now makes the Bode plot go down by 60. So if at 10 we are at negative 34, at 100 we should be at negative 34 minus 60, which is negative 94. We should be roughly at negative 94 decibels, because this slope now is negative 60 dB per decade. Here we are at 34. 34 minus 60, because we moved on by a factor of 10, is negative 94. Very well. Now let's look at the phase. The phase at low frequencies is the same, it's only affected by the gain, which means that the phase at low frequencies is 0. When you reach 1 radians per second, we have two poles, each adds negative 90 degrees. The phase jumps to negative 180 degrees, negative 90 per pole. And we will stay at that value up to the next cutoff frequency, which is 10 radians per second. This comes from another pole, hence another change of negative 90 degrees. We are now at 270 degrees, and this is the final phase of the system. Of course, this is an approximation. Now we need to interpolate this phase, and the interpolation should look like something like this. Passing by negative 90 degrees here, and passing by negative 225 degrees halfway through 180 and 270. Here we have the Bode plot for this specific function. Now let's look at this Bode plot. If we take this system and put this system in a closed loop feedback system like this one, is this system closed loop stable or unstable? Clearly it will depend on the value of k, because now the phase and gain margin here are visible. The gain margin will be negative 180, where we cross 180 around here, and we have a maximum value of k before this point goes up to 0. And the phase margin is at the crossover frequency, we are around here. When you go down, we are at negative 90 degrees around, so we have around 90 degrees of phase margin, which is relatively comfortable. But if we change the gain too much, this gain k, the Bode plot will go up and down here, and we may cross the point of 0 decibels and 180 degrees of phase, and the system may become closed loop unstable. Alright, so this analysis suggests that there is a maximum value of k that will make the system closed loop unstable. Is this true? Well, a quick way to check that is to look at the Routh locus. So let's draw the Routh locus for this system. We have two poles at 1, and we have a pole at negative 10. So the Routh locus for this system, we have a centroid around here. One of these poles will go that way, the other one will go downwards, and the pole at negative 10 goes to negative infinity. This indeed suggests that there is a maximum value of k that makes the system unstable. When you reach this specific point here, for a certain value of k equals k1, what are we looking at on the Bode plot? On the Bode plot, we should see the perfect combination of 0 decibels and 180 degrees of phase. The system is marginally stable here, should be marginally stable there. It is very likely that when we reach this value of k, we are looking at this specific point here, 180 degrees of phase shift. If you go up, the Bode plot that is now here will be shifted up by a certain amount. We're looking at a Bode plot like that, and we'll be crossing 0 decibels exactly at 180 degrees of phase shift. So what is this mystical value here that makes the system closed loop unstable? That's the gain margin. It's simply the gain margin that we are going to calculate later. We can use the whole story here to calculate the gain margin, or we can use the Routh Hurwitz and determine this point based on the Routh Hurwitz. If you take this value of k using Routh Hurwitz, take 20 log of that, it's the gain margin. This means this is an indication of how much we can move the Bode plot up and down before the system becomes closed loop unstable. Okay, we'll determine these numbers later. Now let's take advantage of the Bode plot that we have here and come up with the Nyquist plot first. Now let's go from the Bode plot to the Nyquist plot. At very low frequencies, the phase is 0 and the magnitude is 6. So we are sitting on the positive real axis at 6 decibels. Remember that this is now in regular scale. So this is actually the inverse. How did you get 6? That was 20 log of 2. So this point here is 2. And this is point P1 is here and here. A phase of 0 and a magnitude of 6 dB or 2. Now let's start to increase the frequency. As we go on with the frequency, there is a strategic point here at negative 90 degrees. Why this point? Because this is the point where we cross the negative real axis. If you now go up and look at the magnitude, the Bode plot, the magnitude should still be positive, should be around here. So let's call this point P2, and here P2. At P2, we have a phase of negative 90 degrees, and we have a magnitude that is greater than 1. What exactly it is, doesn't matter at this point. So it should be at around, let's say here, this is point P2. Let's continue to increase the frequency. Now we can cross the point where the phase is negative 180 degrees, somewhere around here. Why this point? Because at negative 180 degrees, that's where we cross the negative real axis. And this is very important because you're now watching for encirclements of negative 1. So at this point here, let's look at a rough estimate of the magnitude. And the magnitude at this point that we're going to call here P3 is smaller than 1. The magnitude of G at P3 is smaller than 1, and the phase is negative 180 degrees. If the magnitude is smaller than 1, how do I know the magnitude is smaller than 1? First of all, because here we have a negative value in dB. If this is negative dB, we took 20 log of a number that is smaller than 1. That's the only way you get a negative value in decibels. We are taking 20 log of a number that is smaller than 1. This was covered in the past few lectures. So, by looking at P3 at negative 180 degrees, we look at a negative value in decibels, and therefore we can conclude that the magnitude of G is smaller than 1. This is very, very important because now we know that we are to the right of negative 1. We should be around here, P3. And now let's keep going. When you keep going, now the next frequency that we cross that is strategic is 270 degrees, negative 270 degrees. And by crossing that value, I actually mean being tangent to that value in the phase, because if you look at the Bode plot here, we are never actually crossing negative 270 degrees. We are tending to 270 degrees as the frequency tends to infinity. So let's call that point P4. At point P4, the frequency tends to infinity, the magnitude of the transfer function tends to 0, and the phase of the transfer function tends to negative 270 degrees. So I'm saying that the magnitude of the transfer function tends to 0. Why 0? Because again, if you look at the magnitude of the transfer function, we see that the magnitude is tending to negative infinity decibels. How do we get negative infinity? Well, we must be taking 20 log of a very, very small number that is tending to 0, and that's what gives negative infinity decibels. So, as frequency tends to infinity, the phase tends to negative 270 degrees, the magnitude tends to 0. And that's the point P4. So where exactly is P4? Well, we are at negative 270 degrees. So we are along the positive imaginary axis, but the magnitude tends to 0. So we are along the imaginary axis at 0. There it is. This is P4. So now that we have inferred all these points from the Bode plot, we can connect them. We went from P1, P2, P3, P4. We are increasing the frequency, so we are going to go counterclockwise and tend to P4 following the negative 270 degree asymptote. Because Nyquist plot is always symmetric with respect to the real axis, we can now close the loop like that and just mirror it with respect to the real axis. This is going counterclockwise. So what can you conclude from this analysis? We can conclude that as it stands right now, the system is closed loop stable. Again, if we put G of S in a unit feedback loop, such as this one, when k equals to 1, we have this Nyquist plot and we have this Bode plot. They are both stable. They are both closed loop stable. But notice that as we increase k, the Bode plot will go up and eventually reach the crossover frequency at negative 180 degrees. The system will be marginally stable. What happens here? As we increase k, this point P3 and this point P1, they will expand. And if they expand, eventually point P3 will touch negative 1. And if you keep increasing that, negative 1 will now be encircled in this loop by the Nyquist plot, and the system will become closed loop unstable. How many unstable poles we have in the open loop transfer function? 0. So P equals to 0. How many encirclements of negative 1 we have? Well, right now we have 0, so the system is closed loop stable. But if this point P3 gets to the left of negative 1, then you have 2 encirclements in the clockwise direction, which means that N will become 2, and z will become p plus n, which is also 2. We have two unstable closed loop poles. And this is exactly what you saw in the root locus. If you go back to a couple of minutes ago when we were looking at the root locus, we will see that the root locus past a given gain had also two unstable poles on the unstable region. This is exactly what you see on the Nyquist plot here. What is this value that we need to add to the system to make point P3 go to 1? It's again the gain margin. If this distance is the same distance that the Bode plot will go up, but here the distance is not in decibels, here it is in decibels. If you need the Bode plot to go up, say, by 20 dB to make the system unstable, that's equivalent to saying that we have to multiply this by 10, not 20 log of 10 is 20, 10 to make point P3 go to -1 and make the closed loop system unstable. So they are both in agreement and they tell the same story. Now that this analysis is concluded, let's actually put a number on these values of phase and gain margin, and let's see what the exact range of stability of this system is. Alright, now let's calculate the phase and gain margins for this transfer function. We can start by looking at the magnitude of Gj omega, which is 20 divided by square root of omega plus 1, omega squared plus 1 squared, all squared, because of the square there, times the square root of omega squared plus 10 squared. This is the magnitude of the transfer function, and we know that at the crossover frequency, the magnitude is 0 decibels or 1. 20 log of 1 equals to 0. We can now use the software to solve for this crossover frequency. This will result in a fourth order polynomial, so use any software to find the answer here. You will not be expected to solve this during a midterm or final examination. So if you solve for omega here, omega is, the crossover frequency is approximately 1 radians per second. So 1 radians per second makes sense. 20 divided by this is 2, so we have 10 times 1 squared plus 10 squared square root is around 10, so 10 divided by 10 is 1, so that is correct. Omega is approximately 1 radians per second. Now we can determine the phase of this transfer function at the crossover frequency. Let's call this omega c. The phase is the phase of all zeros, 0, minus the phase of all poles, A10 of imaginary part is omega, divided by the real part is 1. And here we have two poles at 1 radians per second, so this is times 2. Minus A10 of imaginary part is omega, divided by 10, real part. And when we evaluate the phase at 1 radians per second, at omega c, crossover frequency, this gives around -95 degrees. Now we can evaluate the phase margin as simply how far we are from 180 degrees. That is 180 minus the phase of the transfer function at omega c, at the crossover frequency. And this is 180 minus 95, which is 85 degrees. This agrees with the observation we had on the Bode plot. By visual inspection, we concluded that it was around 90 degrees, and indeed it is. It's 85 degrees, is close enough. This is a positive number, this is good news, the system is closed loop stable, which is exactly what we concluded from the root locus for k equals to 1, and exactly what we concluded from the Nyquist plot when k equals to 1. Now let's look at the gain margin, see how much we can increase the gain before the system becomes unstable. Okay, now to do the gain margin, we have to split this function into real and imaginary part. Let's start by replacing s with j omega. And now we can multiply out this denominator. Remember always that a j times j is -1, j times j times j is -j, and so on. I'll just give the result of this manipulation here. That is very simple math. And here we can split the real and imaginary part of the denominator. We group the real part and the imaginary part. Now we need to get rid of this complex part in the denominator. We can simply multiply the function by its complex conjugate. That is the same denominator, but now with a flipped sign for the imaginary part. And of course divided by the same thing. If you now multiply these two parts, we can clearly see that a j times j becomes j squared. The imaginary part disappears. We have no use for this extensive calculation in the denominator. Let's keep it for later. All we need here is the imaginary part of the transfer function. And now by doing this, you can clearly see that the imaginary part in the denominator disappears. This falls into the category, if you call this a and you call this b, this is a, this is negative b. We have a plus b times a minus b. This is a squared minus b squared. B squared is this entire part including j. And when j is now squared, that becomes negative 1. The imaginary part disappears from the denominator. We can now multiply these two functions. We can identify clearly the real part, 20 times this, and the imaginary part is 20 times that. When you do the gain margin, we are looking for a point where the phase of the transfer function is negative 180 degrees. At that specific point, the imaginary part is 0. We are lying on the negative real axis. The imaginary part of the transfer function is 0. So you are only concerned with the imaginary part of this transfer function. That is negative omega to the power of 3 plus 21 omega times 20 divided by a squared minus b squared. And this is 0. The imaginary part is 0. So now we can have negative 1 divided by a squared minus b squared. We can send that to the other side of the equation, even times 20. So the whole thing times 0 is 0. And we are left with negative omega to the power of 3 plus 21 omega equals to 0. There are three solutions to this. The first one is clearly omega equals to 0. This is not a valid frequency. The other one is omega equals to square root of 21, and this is negative 4.5 and plus 4.5 radians per second. 0 is not a valid frequency, negative 4.5 either. So the solution here is 4.5 radians per second. This is the point in the transfer function where the phase is negative 180 degrees. On the Bode plot, that's where we cross the negative 180 degree line at 4.5 radians per second. Now we can evaluate the magnitude of our transfer function at that frequency. Basically, we are going from the point where we cross negative 180 degrees up to the magnitude, and we are checking the magnitude. How do we find that? Well, that's simply the magnitude of j omega when omega equals to 4.5. And you know that the magnitude is 20 divided by square root of omega squared plus 1 squared times the square root of omega squared plus 10 squared. And when you replace 4.5 here, this gives a magnitude of 0.08. The gain margin is simply negative 20 log of that 0.08, and this is approximately 21 decibels. What does this beautiful result mean? It means that we can add 21 decibels to the Bode plot, and if we add 21 decibels to the Bode plot, the entire Bode plot, the magnitude shifts up, and when it shifts up at negative 180 degrees, the magnitude will be exactly 0 decibels. The magnitude will be exactly 0 decibels. And then the system will become closed loop unstable. Very well. How can you relate this to the Nyquist and the other stuff we saw before? We remember that the Nyquist plot looked like this. Something like that. And this point here was point P3. We had negative 1 there. Where is this value? Well, this value, remember, has a phase of negative 180 degrees, and this is the magnitude. If this is the magnitude, then here we are exactly at 0.08. Ha! Interesting. That's 0.08 on the Nyquist plot. How do we make 0.08 now that this point shift to 1? Well, we have to multiply the transfer function by 1 over 0.08. If you multiply the transfer function by 1 over 0.08, then this point shifts to -1. We are encircling -1 twice. The system will become closed loop unstable with two unstable poles. What is this? This is actually the value of k. If k equals to 1 over 0.08 there, what are we doing? We are multiplying the transfer function by this amount. We are shifting the Bode plot up by 21 decibels. We are making the Nyquist plot go from this point to -1, and the whole thing becomes closed loop unstable. Where is this point on the root locus? This point on the root locus is the point where we cross the imaginary axis. Remember, the root locus we saw before had something like this. What is the value of k here? Is 1 over 0.08. At that specific value, we have two unstable poles. So is there really 1 over 0.08? Well, let's check that with Routh Hurwitz. If you want to check the Routh Hurwitz, we need to take the closed loop transfer function and look at the characteristic equation of the closed loop transfer function, which clearly is s plus 1 squared times s plus 10 plus 20k equals to 0. This is s squared plus 2s plus 1 times s plus 10 plus 20k. If you now expand this, we get s to the power of 3 plus 12s squared plus 21s plus 10 plus 20k equals to 0. Now we can do the Routh Hurwitz array, S3, S2, S1, and S0. Here we have 1, 12, 21, 10 plus 20k. This value here is 0, so this value here is 10 plus 20k, and this value here will be A. A is 10 plus 20k minus 21 times 12 divided by -12. If you equate this to 0, we have 20k equals to 252 minus 10, 242. K is 12.1. What is 1 over 12.1? Guess what? 0.08 approximately. Interesting, isn't it? So this is the maximum gain we can multiply the system by to make the system closed loop unstable. Now we did a very comprehensive analysis here. We had the Bode plot. We concluded from the Bode plot that there was a maximum gain before instability. We did the Nyquist plot and realized on the Nyquist plot that after a certain gain, the system will indeed become closed loop unstable with two unstable poles. We looked at the root locus. The root locus says the same thing. Past a given value of k, the system has two unstable roots. What is that value of k? Well, from the phase margin, we concluded that it was 21 decibels, or 20 log of 0.08. This means that if you add 21 decibels to the system becomes closed loop unstable. How do we add 21 decibels to the system? Well, we'll multiply the system by 1 over 0.08, which is around 12.5. When we multiply k here, when you change k here by 12.5, the entire Bode plot goes up, and then there will be a particular combination of -180 degrees and 0 decibels, which will make the system closed loop unstable. We see that in the Nyquist plot as well. This point here, where the Nyquist plot crosses the negative real axis, is indeed 0.08. So again, if you multiply this by 1 over 0.08, this point goes to -1. The system is closed loop unstable with two unstable roots. And finally, to conclude all that, we looked at the Routh Hurwitz. The result of the Routh Hurwitz was that when k equals to 12.1, which is 1 over 0.08, very close. Well, the numbers don't match exactly because this should be 12.5. They don't match exactly because of the approximations we did when solving this here, but they are very close. We have an entire row of zeros. We have anything greater than 12.1 will make A negative. We have 2 sign changes. The system has 2 unstable poles. When k is exactly this, then we have a row of zeros. We have the Nyquist plot touching -1. We have the root locus touching the imaginary axis. And we have the Bode plot shifting up by 21 decibels and making its crossover frequency exactly happen at -180 degrees. So all these analyses tell the same story.